Today, about 122,000 people are on the donor organ waitlist in the United States alone. Every single day, about 22 people waiting for a donor organ to be replaced inside of their body. Although we've come a long way as a scientific and medical community from the very first organ transplant that was conducted way back in the 1950s, we're still faced with a massive shortage of donor organs. This problem is actually getting worse and worse as time goes by, and we're seeing a widening gap between donor organ supply and demand. What if replacing damaged or malfunctioning tissues and organs inside of our body was as simple as this iconic scene from the Hollywood movie, The Fifth Element? Just imagine, no organ wait list. A doctor would simply take a sample of cells, perhaps from your blood. These cells would be taken to a lab and reprogrammed to become maybe liver cells, heart cells, or kidney cells. These cells would be put into a machine called a 3D bioprinter, and an entire organ would be custom built just for you. After a few weeks, this organ will have grown and matured and be ready to put into your body to replace a damaged or malfunctioning organ. What's so powerful about this technology is that that organ would be made up of your own cells, so no chance of rejection. I know this may sound like science fiction, but I'm here to tell you today that this is already becoming a reality. Our company, Aspect Biosystems, is developing and commercializing advanced 3D printing technology that is capable of producing human tissues with the ultimate vision of enabling the creation of human organs on demand. Now, although we're several years away from this and further scientific development and collaboration will be needed to get us to that future, the question is, what can we do today? Well, before bioprinting technology is used to tackle on the bold challenge of donor organ shortage, we see early opportunities where bioprinting technology will play a key role in helping us advance therapeutic development. So currently, when we look at therapeutic and drug development, we see that it takes over 12 years and $2.6 billion to develop just one single drug that works in humans. Let me walk you through the drug development process. First, drugs are tested on cells in a petri dish and on animals. Drugs that make it through this preclinical stage enter clinical trials where they're tested on human subjects, and only 1 out of 10 drugs is ultimately successful and makes it to the market. Not only is failure extremely common in drug development, it's really expensive. It costs about $200 million per failed drug in the clinic. Even when a drug demonstrates that it can cure human disease, it may not work for you. This is because your body is unique. A drug that will cure the person sitting right next to you will cause detrimental side effects in your body. So how do we solve this problem? How do we increase the success rate in clinical trials and get effective drugs to you quicker? Well, what if we could engineer human tissues, a part of a real person but outside of their body, and test drugs on these tissues before clinical trials? If we can do this, we can more accurately determine if a drug is safe and effective before clinical trials. Now, I'm a biomedical engineer, and as far back as I can remember, I've been intrigued by how things are built. And when I think of engineering, I think of building things from the ground up. When I think of biology, on the other hand, I think of dissecting the human body down to individual cells. Think of these cells as the building blocks of your body. Our understanding of these building blocks is rapidly advancing. Biologists have taken the human body apart. Now we could combine engineering and biology to rebuild different parts of it. By combining different disciplines and collaborating, we can tackle the world's most pressing issues. And this is precisely our story at Aspect Biosystems. Engineers, scientists, clinicians, all working together to develop an advanced printing technology that allows us to create human tissues. Here's a picture of a human tissue where each hexagonal shape represents a single cell or a building block. Well, what if we wanted to print a part of a lung, an airway, for example? Well, we'd start off by designing a 3D computer model of an airway. This model would then be printed layer by layer using a machine called a 3D bioprinter. Instead of using plastics or other non-living materials used in standard 3D printing, we use real living human cells. We combine these cells with other scaffolds to provide a suitable and comfortable environment for our cells to grow. These cellular materials then become our inks, kind of like the inks we use in conventional desktop printers. We now have our building blocks and are ready to construct our tissue. So how do we deposit these living inks? Because tissues are made up of many different components, we need to handle many different materials at once. You may be thinking of a lab filled with biologists mixing and preparing different materials, and they would be doing this by hand. This would be slow and manual. They would need access to a lot of equipment, different tools and dispensers, and they would need to switch between these different tools, dispensers, and equipment throughout the process. This would be extremely manually intensive and error-prone. What if we could integrate and automate many of these lab functions and shrink them down to one simple chip? This is exactly what we've done, and we call this chip Lab on a Printer. I brought one with me today. I'm holding one in my hand right now. It's about the size of a USB stick. Our Lab on a Printer is the core of our bioprinter. So our bioprinter uses this Lab on a Printer to deposit living inks. It takes multiple different living materials and deposits combinations of these on the fly through a single nozzle to rapidly build customized living structures. Here's an example where our Lab on a Printer is switching between many different materials at once. We've labeled them different colors here, but these could represent different cell types, growth factors, extracellular matrix content, and other key components that make up the tissues inside of our body. Our Lab on a Printer then deposits these living materials layer by layer to construct our living structures. This tubular structure could be an example of a blood vessel or an airway. Now, after printing these structures, they are incubated over a period of time, and throughout this process, the cells within these structures begin to talk and communicate and form interconnected networks. If we actually zoom into one of these printed structures immediately after printing, you see many green dots. Each one of these dots is a single cell. Here's how they looked after several days. Because we provided a comfortable environment for the cells to grow, they begin to interact and form these interconnected networks. Our 3D printed structure has transformed into real living human tissue. Now, although we're several years away from printing entire replacement and fully functioning organs, what we can do today is we could print smaller parts of these organs, like I just demonstrated, and we can use these tissues to study disease and to develop novel drugs. For example, we took muscle cells from a donor lung to construct an airway. We took these cells and we built them up into tubular structures, similar to the one I just showed you. So during a real-life asthma attack, our body releases a compound called histamine. This causes the muscle tissue that wraps around our airways to contract. It reduces airflow and causes asthma patients to have trouble breathing. We dosed our bioprinted airways with histamine and they began to contract, just like the airways of an asthmatic patient. So we recreated an asthma attack in one of our printed tissues outside of the body. We then treated it with a common anti-asthma drug found in inhalers, and they began to relax, just like the airways of an asthmatic patient. So imagine the possibilities of using these bioprinted tissues to study disease and develop novel therapeutics. In fact, we're working with global biopharmaceutical companies now to do just that. As individuals, we are all different, and the diseases that we suffer from affect us in different ways. Asthma, for example, is a complex syndrome with many underlying causes, and different people react differently to the same drug. This is true for many other diseases, including heart disease and cancer. The beauty of bioprinting technology is that we can build tissues using your own cells and test drugs on these personalized systems so that we can determine a therapeutic that is custom to your own makeup. Bioprinting will ultimately enable us to create entire replacement and fully functional organs. This will have profound implications on medical practice and enable us to close the gap between donor organ supply and demand. But way sooner than that, bioprinting technology will really enable us to have a significant impact in determining the human response to drugs. What this means is that we could eliminate drugs that won't work in humans sooner and take drugs into clinical trials with a much higher chance of success. Ultimately, bioprinting will enable us in the very near future to develop better, safer, and cheaper drugs. Now, to solve some of the biggest health issues and issues in medicine, I believe we need to have a collaborative approach where we're bringing in multiple different disciplines, perspectives, and backgrounds. This is exactly what we've done at Aspect Biosystems, where we brought in multiple different people with different backgrounds in engineering, science, people with clinical backgrounds, people that have expertise on the regulatory side, on the policy-making side. And I believe it's this collaborative effort that is allowing us to continue to innovate and to develop solutions that will ultimately have a meaningful impact on patients. Whether that's diagnosing and finding cures for cancer, developing replacement tissues that will allow us to live longer and more active, or finding cures for currently life-threatening diseases. These are some of the big challenges that we're solving through bioprinting technology, but also importantly, we're solving through collaboration. So as the world gets more and more advanced, I also think it becomes more complex. And we owe it to the world and to humanity to stay ahead of our challenges and to keep on collaborating and innovating so that we can solve some of these issues that are core to our ultimate existence as a species. So whether that's accelerating the development of novel drugs and defeating disease, exploring how growing energy demands could be met in a sustainable way, or discovering the furthest frontiers in our universe, when we work and come together in a collaborative manner, we can overcome our global challenges. Lastly, I'm continuously inspired, optimistic, and hopeful about our future. I think there's no better time to be alive than today, with all of the great knowledge that we have and with all of the great minds like the ones that we have in our room that are motivated and focused to ultimately enhance our collective human condition and to pave the way to a better future. Thank you very much.